Hi, I'm Nicholas,
And I'm Lawrence.
and we're here to talk to you about SmartCook, our product for temperature sensing for culinary applications with smartphone integration. The problem we would like to solve with our product is the fact that it's very difficult to know the precise temperature of a stovetop when cooking on a stove. Part of this problem is that the typical pre-existing technology to solve this issue is a stovetop dial, as you see pictured on the slide. And this effectively allows you to set the temperature to somewhere between 0 and 10. Now, what does this value actually tell you about the temperature of your cooking surface? Not very much. All you really know is that hopefully when you set it to a higher number, the surface is hotter. To make matters worse, there's no standard, as far as we know, among stove manufacturers that 6 on one stove equals 6 on another. So if you're using one stove to another, there's most likely no even transition for the temperature settings you use. Now, in addition to the stovetop temperature dial, there's some existing technology that could be used to solve this problem already, such as a thermometer, which you could put in your food to measure the temperature. However, I think most people who are cooking would probably not want to do this as it's time consuming. The thermometer would have to be cleaned after, and it's just not all that practical. A digital meat temperature sensor, as you also see pictured in the middle, could also be used to help solve this issue. However, again, it needs to be in contact with the food, and although a little more practical than a thermometer, it's still not easy to use, and most people wouldn't use it day to day while cooking. Most people these days also have smartphones, and although this isn't currently part of the solution of the problem, we think it could be.
So after analyzing this problem and taking a survey of the existing technology out there, we tried to come up with a list of the desired features that we would want in our ideal solution. And those were accurate temperature detection, low cost, so we wanted to create a product that most consumers could afford, easy to use, so we wanted our product to be intuitive and easy to pick up for a variety of people, and versatile. We wanted our device to work with a variety of smartphones, tablets, other smart devices, and as well with a variety of different cookware, frying pans, other cookware. But as well, we had to weigh these ideal features with certain trade-offs, and those were primarily cost and development time. So with those ideal goals, we came up with some primary design goals that we decided that if we met, our project would be deemed a success. And those were measurement accuracy of 5 degrees with a stainless steel pan. We felt that this would be sufficiently accurate for cooking applications. An easy to use attachment and detachment mechanism, which would allow our device to attach to a variety of cookware. Wireless communication of over a meter, so essentially enough range so that it would be easy to use. Display of temperature measurements in an Android application, essentially an interface which allows a consumer to easily use our hardware. And as well, in that Android application, have certain notifications. Sorry?
Okay, hold on. It's for the camera.
Oh, okay.
It's already turned on.
Oh. Sorry, and as well, have certain notifications in our Android application of temperature events. So for example, your pan is now hot enough that you can place food in the pan. So to meet these design goals, we came up with this integrated hardware and software solution that we've dubbed SmartCook. And you can see a rendering of our device here in the bottom right corner of the screen. Our device sits on the handle of certain cookware and attaches to it using an adjustable clamp. It uses an IR sensor to detect the temperature of the pan and uses Bluetooth to communicate with smartphone. And it also has a smartphone app which allows the user to interface with our hardware. So the primary principle behind how our device works is this idea of blackbody radiation. Essentially, it's a phenomenon where bodies emit electromagnetic radiation, which is dependent on their temperature. So you can see in this plot here the various spectra of different black bodies at different temperatures. So you can see at 5,000 Kelvin, it's roughly in the visible range, but as the temperature decreases, it shifts more towards the IR range. So when we're talking about temperatures not of the sun, but of closer to what we'd see in a kitchen, it's mostly in the infrared range. So This is essentially what we use to measure temperature in our device. We measure the amount of IR energy emitted from a pan, and from that we can calculate the temperature of the pan. Another important issue that I should talk about here is the idea of emissivity. It's the idea of, it's a material property that dictates how much material deviates from this ideal diagram here. So our device, in terms of hardware, consists of 4 major components: the IR sensor, which does the temperature sensing, a microcontroller, which interprets the signal from our IR sensor and sends it to our Bluetooth device, the Bluetooth module, which does the communication with the smartphone, and as well a mechanical enclosure, which houses the previous 3 systems. So the most important component of our hardware system is the IR sensor. It's a Melexis MLX90614 sensor, and we chose it primarily for its high accuracy as well as low cost. It essentially contains 3 major components: a temperature measurement system, which composes of a membrane and thermocouple system. How it works is that a thin membrane absorbs energy in the IR spectrum, and this absorbed energy causes this membrane to heat up. Thermocouples attached to this membrane measure this change in energy. And in addition to that component, there's optical packaging, essentially a lens you can kind of see in front of the sensor, which helps to remove some of the unwanted wavelengths, as well as it helps to focus the sensor and narrow the field of view. It also contains an integrated circuit, which helps with signal amplification and noise reduction. The output of the sensor is something called a PWM format, or pulse width modulation. And you can kind of see an example of the signal here in the bottom right. The idea is that the data is sent in pulses, and depending on the width of the pulse, that's related to the data essentially. So the other 2 components are the Arduino Rev3 Uno, which is the microcontroller for our system. It's kind of the brain or the computer of our system. And it's a cheap, popular, well-documented, and open source piece of hardware. It's commonly used for different projects. What's great about it is it allows us to easily read the PWM output from our IR sensor and convert that output into a serial output. So instead of these modulated pulses, we convert it to this binary stream of data, which can be interpreted by our Bluetooth module. So our Bluetooth module sends this serial output to the smartphone. So the last component of our hardware component of our device is the enclosure. We designed it using standard CAD software and had it 3D printed, primarily for low cost as well as fast turnaround time. It serves to essentially fixture all of our electronics in the device. You can see that in the bottom right corner here, as well as protect the electronics from outside sources of damage. It has an adjustable clamp at the bottom, which allows it to attach to a variety of different cookware, and as well has opens up so you can access the battery, and has an on and off switch so you can conserve battery life.
We also have a set of software requirements, which effectively comes in 2 sets. There's the requirements for the Arduino software, and that is essentially responsible for reading the PWM signal from the infrared sensor. It must then convert that signal into something that we would understand and can be sent through a binary stream to the Bluetooth module, and must then actually send this data to the Bluetooth module. It will then delay an amount of time and repeat this process. The smartphone software requirements are a little more complicated. It is responsible for initially establishing the Bluetooth connection between the Bluetooth module and the smartphone. It must then receive the temperature data and display the most recently received temperature data as it receives it. We would also like to have this application enable user-settable temperature notifications, such as Lawrence previously described. When your pan heats up to whatever temperature you would like it to be for cooking, it will let you know, so you know that you are ready to start cooking. There are also several important software design decisions involved. One of the most important and user-facing is the design of the user interface. We decided that simplicity would be best in this case because We really do have a simple goal in mind. We just want the user to be able to know the temperature of their cooking surface. So for this reason, all that really is displayed normally is the temperature, or if the device is not currently connected to the Smart Cook device, then there will be a notification that tells you this. And as you can see in the left-hand screenshot, you may use a menu to connect to a device or set temperature notifications. Once it's connected, as you see on the right, the temperature will be displayed. Another important factor to be considered was the frequency of temperature transmission from the Arduino to the smartphone. Now, we don't want this to be too infrequent, otherwise the application is essentially useless because the user will not know their temperature in enough of a real-time fashion. However, if it's too frequent, the battery will be drained unnecessarily on the Arduino and on the smartphone. For this reason, we settled at 1 second, as we figured this was more than enough for the typical culinary applications it would be used for, and it should also not overly drain the battery. Last but not least, there's the matter of how do we actually initiate the Bluetooth communication between the smartphone and the Smart Cook device. We initially considered, for added convenience, having the connection be automatically established when one opened the app. The issue with this approach is that if the user is unaware that the app is still open and the device is not near, it may be continually searching for a device, and on Android, this is a very costly operation and would unnecessarily drain the user's battery, and no one wants to end up with a dead smartphone after an hour into the day. So that's why we decided that it would be best to have the user specifically tell us when the app should try to connect, and so that's the way we have done it.
So we did a variety of tests to essentially verify our design to ensure that it met the goals that we set out. The three major tests that we did that we're going to talk about today are Bluetooth range, how the sensor accuracy was affected by distance, and the typical device operation compared to a commercial IR temperature gun. So the first of these tests was the range of the Bluetooth. Essentially what we did was we increased the transmission distance between our device and the smartphone until Bluetooth communication ceased to work correctly. We determined this distance to be roughly between 20 to 30 meters, which was a lot larger than our initial goal, and it should be far more than sufficient for the typical kitchen application. The next test that we did was a comparison of how the sensor's accuracy is affected by range. We used a beaker filled with ice as essentially a temperature standard, or essentially a temperature target, and we moved our device further away from the beaker until the accuracy of our infrared sensor fell below our intended spec. And we found that within the typical range of operation for our device, the distance between our device and the pan of roughly 10 to 20 centimeters, that our infrared sensor was much above our quoted spec of plus or minus 5 degrees Celsius.
The last test we did to verify our device was verification of the actual temperature readout in our typical operation pointing into the pan. The test you see the results of shown on the screen is with a thin layer of olive oil, which helps replicate a standard or more likely cooking scenario than an empty pan. As you can see, we were within plus minus 5 degrees of the readout from the IR gun for the whole experiment, and we therefore deem this a success. Since all of our verifications proved successful, we've deemed that we were successful in meeting our prototype requirements, and our prototype was a success. We have several further applications in mind for what this product could be used for, one of which would be scientific research where temperature-dependent process should be monitored. Another would be manufacturing processes where there's a temperature-critical process. Essentially, anytime you want to be remotely notified of a temperature, this product could be useful. We're also aware that there are several improvements we could make to our product. One of which is we'd like to do further verification with additional pan types and foods in the pan, as we did not test this extensively. We would also like to design a printed circuit board to house the actual Arduino integrated circuit and other components that are currently on a prototype circuit board. This would in turn allow us to make the device much smaller and more convenient to use. We could also take it a step beyond that and actually integrate the temperature sensor and Bluetooth module into the pan, as this may prove even more convenient to some users. Last but definitely not least, there are several improvements that we would like to make to the smartphone application. One of which is we would like to include a graph of the temperature over the past half hour. That way, if you are not actively monitoring your phone the whole time, which you probably won't be, you can look at it and know what the temperature activity has been like. Additionally, we'd like to include a small list of ideal cooking temperatures for various foods, again for added convenience, so the user doesn't necessarily need to go look up those things when they're curious what temperature they should use.
So we have several acknowledgements that we would like to give out of the many people that helped us throughout our project. First and foremost, Dr. Safavi Naini, our faculty consultant, who gave us invaluable guidance and help throughout our project. Jen Kogan, who helped with a lot of the behind-the-scenes administrative work. And Dr. Aziz, as well as Dr. Barbie, for helping to coordinate the different courses involved with our program. These are just citations for the images used in this presentation. And that concludes our presentation. Thank you guys for listening, and at this point we'd like to open the floor to questions. If there are.
Thank you very much. We have time for a few quick questions. So,
What if you're using a pot? I mean, then you can't see the surface of the pan, you can't take the temperature. So.
Currently, our device is definitely optimized for a pan. For a pot, we would most likely need to integrate some sort of, angle control mechanism at the hinge that it attaches to. That way, you could mount it at the handle and then tilt it into the pot as needed. Currently, this is not something that we could feasibly accomplish in the time we had allotted to accomplish this project.
In addition, I'd just like to add that the primary application we were looking towards is more towards pan types of cookware, whereas in a pot you typically are cooking some type of liquid. You're not necessarily interested in the surface temperature, but with a pan you're typically searing or frying something, so you're more interested in the surface temperature of that.
So in a cooking environment, you deal with a lot of vapors, right? Steam and vapors. So did you guys worry about the vapor condensing on your IR sensor in affecting the readout? Did you consider that?
No, that's not something we've considered deeply. Again, with verification for additional foods, something we most likely need to, is something we'd likely need to consider and possibly add some sort of anti-condensing coating or layer in between the actual IR sensor. That's not something we've considered thoroughly enough at this point.
Just a extension. So how does the user make sure that the IR is focused on the bottom of the pan and not on the sides? That is not blinking. Do you put any optical, you think of putting some optical LED for it to be
Right, so that's not something that we have currently, but that is future work that we've considered. We've considered mounting, for example, a laser pointing at the same angle as the IR sensor, so the user knows exactly where it's pointing, but not for our device, no.
Question on the verification temperature range. You guys use the ice, but most of us would be worried about burning stuff, right? So what is the temperature range you guys verified?
So the temperature range we verified in was when the graph you saw, I'll just, here, this is actually not with the ice. This was our typical conditions. It was heating up the pan with olive oil on it. So it was actually a heated temperature, not a beaker of ice. So for this verification, we believe it is still relevant because it was, an actual heated environment. I do not know off the top of my head the temperatures that were involved, as I wasn't as closely involved with this testing.
It was around 100 degrees Celsius, typically in that range.
So in this
Oil,
graph,
100 degrees C. Usually it's high.
Sorry?
Usually the oil temperature is high. The reason I'm asking is most of the things they don't work the same in different temperature. So
Sorry, most which don't work the same?
Verification temperature, you can see a more complete.
So in this graph, why do you start seeing these oscillations in error after certain time?
What-
It almost looks very periodic.
Right. What we were thinking is that at higher temperatures here, the IR sensor essentially gets less reliable. It's highly dependent on the
Heat flux.
heat flux essentially coming out. So if the temperature is changing rapidly, then we feel that the accuracy of the sensor decreases. And so essentially, if both the accuracy of our sensor as well as the standard is varying, then you get these large deviations here in this difference.
Which probably kind of points you to Professor Tang's question.
Right.
One last question. How is this connected with nano?
So that's a pretty
It's an
pretty
excellent
common question that we got. Basically, when we sat down to meet as a group, we decided to work on something not nanotechnology related. Basically, we wanted to work on something we were passionate about, and we decided on this project.
All right, thank you again.
Thank you. Thanks.